Welcome back. This is week 6 of inverse methods in heat transfer. In the previous video, we saw these two rules of probability. The sum rule, which helps in marginalization. And we saw the product rule. And the product rule connects the conditional probability to the joint probability. Okay, so you can switch between the two using the product rule of probability. We saw that a direct consequence of this was Bayes theorem. In this video, we will basically see, in fact, you can see Bayes theorem as a consequence of both these, as I will talk about briefly in this video. But the main formula is thanks to the the product rule. So we'll see a couple of simple examples. Now, I want to point out these are really simple. We are looking at very simple discrete examples of Bayes theorem. Next week, we'll look at continuous examples directly applied to the inverse problem case. I would recommend that you skip this video if you're already very comfortable with Bayes' theorem. You need not go by my notations. Of course, next week, we'll see more complex examples, and that might be more pertinent to your case if you're already somebody who's very familiar with Bayes theorem. So let's go back to our original problem that we were looking at in the previous video. Once again, a red basket and a blue basket and different distributions of fruits within that. And we want to write down all the conditional probabilities. Remember, F here stands for fruit. And this here stands for the basket. We had made the joint probability table the last time. And we have a few questions. So the next question is, if we pick a fruit at random, what is the probability that it came out of the blue basket? Okay, so I picked up a fruit and I want to know what is the probability that I picked it up from the blue basket. Now you can obviously see that has to be 0.6, but we will calculate it in a slightly different way here. And next we ask the same question, but a little bit more specific. If we pick up fruit at random and it turns out to be an orange, what is the probability that it came out of a blue basket? Once again, please think about the intuition of this problem. If I gave you nothing, if I gave you no information about that fruit, you would say 60% that it came out of a blue basket. If it turns out to be an orange, what is the likelihood that it came out of a blue basket rather than a red basket? This you have to think about. Will it increase? Will it decrease from 0.6? How is the probability affected by this new piece of information that we have? Again, when we come to the next week, we will see how this is relevant there as well in inverse problems, the same idea. Okay, so let's now write down all the conditional probabilities. This is straightforward, but nonetheless, let us first make a joint. I had a joint trial table, but now this is a probability table. So remember, previously we had 30 here, 10 here, 15 here, and 45 here. I have put that back and divided by the number of trials. And now we have made a joint probability table. Now, what does this number mean? This means what's the probability that the fruit we picked was an orange and the basket was red. Okay, so that's what it means. Now here we are going to use our product rule. The product rule, remember, was P of x comma y is P of y given x multiplied by P of x, which gives us P of conditional probability is probability of x comma y divided by P of x. Now notice how intelligently this notation has been chosen. It's almost like a divide, and you can see that that's where it kind of reminds you that you have to divide by x. Okay, so that's just as a useful mnemonic. You can use this fact. P of y given x is P of x comma y divided by P of x. Okay, so we can use the same thing here. Y here could denote the fruit and x here could denote the basket. So you would basically have P of fruit given basket is P of fruit and basket divided by the probability that that basket was chosen. Another way of saying it is, what's the chance that I picked an orange given that it was a red basket? Well, how many cases did I have basket, orange and a red basket? By how many cases did I actually choose the red basket? So it's easier to see it when it's number of cases. Okay, so we write these numbers down. So for example, let's take this first case, P of F equal to O, B equal to R is here. So that is 0.3 divided by P of B equal to R, which is this plus this. Where did this come from? P of B came from the sum rule. Remember, P of B is P of B, comma F multiplied by P of Fi. So you sum over all possible fruits, which is it's an orange and it is an apple. Okay, so once you do that, I'm going to recalculate this once more below. But please do remember this. P of B equal to R can actually be calculated through the sum rule. Okay, so some of you might have seen Bayes theorem also in this form. I will show that later. But P of B equal to R also was given to us originally as 0.4. So 0.3 by 0.4, 0.75. So similarly, we can calculate all these other cases. This would be P of F equal to A, comma B equal to R, which is 0.1 divided by 0.4, which is 0.25. Okay. So similarly, these two. This one is 0.15 divided by 0.6. So this was 0.1 by 0.4. This is 0.15 by 0.6. This is 0.45 by 0.6. So put these together, you can actually write all the possible conditional probabilities. So for example, given that the basket was blue, the probability that you pick an apple is obviously 75%. This straightforward. Given that I am already in this box, I am obviously going to get 75% likelihood that I am going to pick an apple. Okay. We have just done it in a more formal way here, right out of the table. Because really speaking, that's how we operate for large cases. We can't do them intuitively. Okay. Now we have these 4 conditional probabilities. Suppose I ask you what is the probability that the fruit is an orange? Okay. This you would calculate using the sum rule. So we would ask the question, what is the probability that the fruit is an orange? And I'm going to sum over all possible baskets. Okay, the fruit was an orange, it came from the red basket. Fruit was an orange, came from the blue basket. Okay. So if we do that, so you can do this in greater detail using the product rule. So I'm going to write it this way. Fruit is an orange, red basket, and what is the probability of picking a red basket? Fruit is an orange, basket is blue. What is the probability of picking the blue basket? Okay, so first we pick a red basket with probability 0.4. From that, we pick an orange with a probability 6 by 8, which is 0.75. So 0.75 into 0.4 plus 0.6, which is the probability of picking a blue basket, multiplied by 1/4 of those are oranges, 0.25. So summed up 0.45, and you get this 0.45. So similarly, you will get this other probability, which you can do as an exercise. You will get that as 0.55. All these are reasonably simple calculations, but notice this. So this probability can be calculated as from the sum rule via marginalization. Again, all these are fancy terms. Most of you would have done this intuitively, but these fancy terms become useful when we come to the continuous case, and it's kind of not obvious how to do these integrals, etc. So which is why we are doing it in detail, even though you know this in the simple discrete case. Okay. So the second question was, if we pick a fruit at random, what is the probability that it came out of a blue basket? This answer is, of course, straightforward. Okay, so you automatically know it's 0.6 because that was given to us. This given thing is what is known as the prior probability. What is the probability that the blue basket was picked? It's 0.6. So Suppose I similarly say that I am within the rainy season in Chennai, which is where I am right now. What is the probability that it will rain? And it rains practically every day here. So if you go by last year's weather pattern, you will say that in such and such month, it will rain with probability nearly 1, okay, on a particular day. So this would be the prior probability. Now I say something like, you are in Chennai in the monsoon season, but there has been a dry spell. Given that currently there don't look to be any clouds which are being shown on the satellite images, what is the probability that it will rain? Now your probability comes down. So the prior is what you know before, and the posterior is what your condition tells you. Okay, so the recent condition tells you this. Now, this probability also could have been obtained, as we just saw, by just summing these up. Okay, so P of B equal to B, comma F equal to O, and then summing up with via marginalization is also something that you may get as 0.6. Okay, so just purely through the joint probability table without these numbers given also, you can actually calculate these numbers back by summing these up. Okay. Now let's look at the question which we are leading to, which is what we'll use Bayes theorem, which is if we pick a fruit at random, it turns out to be an orange. Then what is the probability that came out of the blue basket? Basically, compare it with the previous question. There was a random fruit. I don't know anything about the fruit. What is the probability it came out of the blue basket? 0.6. Now I tell you something more. I tell you it's an orange, then suddenly the probability changes. Okay, so this probability is now what we are going to calculate. This is the conditional probability that the basket is blue, given that the fruit is an orange. Okay, so that's the probability. Let's calculate that right now. So this is basically a straightforward application of Bayes rule. We'll say, I'm of course making this more explicit. We can say something like P of y given x is P of x given y, P of y divided by P of x. Of course, as we will see, this P of x has further components, as we will see shortly. Okay, so here y is the basket, x is the fruit. So probability of the basket being blue and fruit being orange is the other way around. Probability of the fruit is orange given the basket is blue, which we calculated just now, multiplied by the probability that the basket is blue. This is what is known as prior. If I gave you no information, what is the probability basket is blue, divided by the probability that the fruit is an orange. Now notice how this was calculated. The fruit is an orange was calculated as fruit is an orange given that the basket is red, plus the fruit is an orange given that the basket is blue. Also not given that the fruit is an orange and the basket is red, divided plus fruit is an orange and the basket is blue, which is here. 0.15 plus 0.45 is 0.6. Okay. No, sorry, the other way around. 0.3 plus 0.15, which is 0.15. Sorry, I added the wrong column. Yeah. Okay, so let's calculate these. What is the probability that the fruit is orange given the basket is blue? That's straightforward, 1/4. 0.25, we had also calculated it earlier. The prior was 0.16. And the probability that the fruit is an orange, regardless of which basket it came out of, is 0.45. So the net probability now becomes 1/3. Okay, so what is this 1/3? If we pick the fruit at random and it turns out to be an orange, what is the probability that it came out of the blue basket? It is 1/3. Now notice, the blue basket itself would have been picked up likely at 60%, but we have now reduced the probability to 33%, because if the fruit is an orange, it is more likely that it came from the red basket rather than from a blue basket, where it would have been very, very unlikely. So this is where Bayes theorem helps you. It gives you non-intuitive results. Okay, it's hard for you to say. We might just hear, and I'll show you a next example where it becomes even less intuitive. This was making the rounds during COVID. So Bayes theorem is particularly useful because humans have very poor intuitions about fractions. Okay, our intuitions are good about numbers. We are very, very, very poor at understanding fractions, which is why we tend to get really bad results. If somebody asks this question, I mean, there has been a large scale study, and some people have effectively got the Nobel Prize for showing that our intuition for probability is really, really poor, which is why we automate. As you will see, even in the next week, we automate all systems where we have to calculate probability because our intuition for it is very good. This probability is known as posterior probability. That is, before I knew anything, I said the basket was blue with probability 60%. After I knew that the fruit is an orange, I can now give you a posterior probability that is only 33%. Again, it's sufficient to just make the joint probability table to obtain all quantities, and which is what we'll be doing for the continuous cases. So here is Bayes' theorem. Bayes' theorem, as we just wrote down, is P of y given x is P of x given y multiplied by Py divided by Px. Px, of course, is sigma of P of x equal to whatever xi we are considering. I'm going to make this informal. P of x comma y summed over y. Okay. All possible values of y you sum over. In this case, it was basket was red, basket was blue, etc. You sum over all those possibilities. This is not alpha. This is proportional to. And this is the form in which we will use it in the next week, which is P of y given x is proportional to P of x given y multiplied by P of y. This is known as the posterior, this is known as the prior, and this is known as the likelihood. Now, what are x and y? I mean, x and y typically are used in a form where x given y is a little bit more obvious and this is less obvious. Okay, but they don't have any specific meaning, one or the other. Of course, they will have a specific meaning when we come to inverse problems. So inverse problems, you will see that there is actually cause and effect versus cause. So one of these is the cause and one of these is the effect. And we will see how it makes sense to see both the likelihood as well as the posterior when we come to inverse problems. So let's come to a second example, which is a more recent example. Usually this example is given with cancer diagnosis. I just mildly changed it to COVID diagnosis because that's what went on in the world, this horrible thing over the last couple of years. So this became very relevant when we started looking at the results of RT-PCR tests. As you might remember, many of us underwent these tests, and there will be certain numbers which were given that the RT-PCR test is so accurate, and you want to find out what is the likelihood that you have COVID. And there is also the phenomenon of us doing multiple tests one after the other. Okay. So let's say you're going for a diagnosis. What are the questions we must ask to actually determine the accuracy of the diagnosis? As it turns out, it's not sufficient to just ask for one number. This is the first non-intuitive result that you will get here once you do a proper Bayes theorem analysis. Okay. And given some numbers of the accuracy, what are the chances that the person actually has COVID? So I'm going to make up some numbers. Like I said, these numbers are not so good for COVID tests. COVID test numbers are actually a little bit worse. And you might have heard right now, as we speak about it in 2023, that there have been a lot of controversies about these tests and the efficacies of vaccines. And a lot of it actually genuinely has to do with Bayes theorem. Okay. So if we go and ask, okay, so somebody takes an RT-PCR and we ask, okay, what is the accuracy of this test? It turns out there are two separate questions one can ask. So the first question you can ask is, okay, you did a test. And what percentage of the people with COVID test positive? So this person says 99%. And let's say you got a positive result, you are like, oh, there's a 99% chance that I have COVID, but that would be wrong. That is because, let's say I have a dummy box. And this number is even 100%. So let's say I have a dummy box. For every person, it says COVID positive. Now, 100% of people who are COVID positive will still show COVID positive because it always shows COVID positive. So that test is meaningless, even if it is 100% what we will call sensitive. That is, if I am a person or I have a voice box which keep on saying you are COVID positive, you are COVID positive, of course it will be right for all the people who are COVID positive also, but it will be wrong for a lot of the people, or in fact all of the people for which it is COVID negative. So it's not sufficient to ask only the question about sensitivity, which is what are the true positives. A true positive means the person is positive or the person has COVID, let me use that word, and the test is positive. Okay. But that's only one of the four possibilities. The person could not have COVID and it could still show positive, etc., etc. So you have to ask a parallel question, which is what percentage of people without COVID test negative? Or you can even ask what percentage of people without COVID test positive. But now let us say this also turns out to be 99%. Now you have a more interesting case. Okay, so now you say, okay, 99% of people who have COVID test positive, only 1% of the people, that is from here, this is called specificity. Only 1% of the people without COVID test positive, or 99% of the people without COVID test negative. Okay. But it turns out, and if we do Bayes theorem properly, we actually need a third number, okay, which is what percentage of the population has COVID. And let's say I gave the number 0.5%, which was true about at a certain point of time. You can increase this number to 3%, 5%, 10%, whatever you want, and your numbers will change accordingly. But let's say at a certain point, only 0.5% of the population has COVID, and you go and you check and you get COVID positive in an RT-PCR. And the RT-PCR turns out to be really good in that 99% of the cases, it will test positive if you are positive. 99% of the cases, it will test negative if you're negative. Now, if the question is, I got positive, what is the chance that I have COVID? You might say it is 99%. Obviously, I mean, these two numbers are 99%. Turns out we will be really, really far away because of this number. And that's where the non-intuitive part of Bayes theorem comes in. Okay. So it's important to think what are the random variables in this problem. So here is the question. What are the chances that the person testing positive actually has COVID? So here we now carefully define our random variables. Now our random variables are two things. The state of the disease. Okay. The person either has COVID or has no COVID. And the other random variable is the result of the test, positive and negative. Why are these random variables? Because the result of the test need not always be positive, need not always be negative. As I said, if you remember, a random experiment is something that you can do a few times and you might get different results. Remember, many of us repeated our COVID test. So now what is the data given? Now let's look at our data given very carefully. It says probability that you are positive given that you have COVID, okay, is 0.99. Probability that you are negative given that you didn't have COVID is also 0.99. Okay. Now, no other information is given. This is the prior. I picked a random person off the street and said, hey, what is the probability this person has COVID? You will say, well, it's 0.5%. I have no other information about this person, so it is 0.005. Okay. So the question now is, given these three pieces of information, remember, if one of these three is missing, you actually cannot give a good numerical answer. Okay. Which is why we have to be very careful as intelligent consumers of statistical data. Okay. It can be very confusing even to the expert. This has been checked. Even Nobel Prize winning people make mistakes about probability, elementary probability. Okay. Which is why we have all this machinery in there. So the question is not what is the probability that you will be positive given that you have COVID, but probability that I tested positive, what is the chance I have COVID? Now notice P of plus given C is not the same as P of C given positive. Okay. As I told you earlier, this is an important distinction. Okay. So here is Bayes theorem. a simple Bayes theorem. Okay. So Bayes theorem says P of C given positive is P of positive given C multiplied by PC divided by P positive. Same formula, P of Y given X is P of X given Y, Py by Px. Notice how powerful such simple expressions can be. Okay, it is just remarkable. The power of mathematics here is remarkable that it can clarify so many things which we would have gotten confused about. Okay, so let me go further. P of C given positive is this divided by P positive. Okay, remember it's summation over all the possible cases. So what are the possible cases? You could be positive and you could have had COVID, or you could be positive and you might have not had COVID. These are the only two possibilities. Now this further by the product rule is your positive given COVID by the probability that you had COVID, positive no COVID multiplied by the probability that you have no COVID. That's what we have in the denominator here. Once again, to clarify, this is positive with COVID, this is positive without COVID. Okay, so now let's plug in the numbers. P of plus given C was 0.99, P of C was 0.005, P of plus given COVID 0.99, this is 0.005, and P of positive given you had no COVID is 1 minus the possibility that you had negative with no COVID. Okay, this should be straightforward. If I had no COVID, I would test positive when 0.01 times. So suppose this was 0.95, then P of positive given no COVID would have been 0.05. Okay. So the conditional, the denominator has to be same, only then we can do the 1 minus. Okay, I should put a bracket sign here. Okay. Multiplied by what is the probability that you had no COVID at all? 99.5% chances are without any other information, I don't have COVID. Now I put these numbers, you will see that if you do the calculation, this number is approximately twice this number and you get 0.33. So there is only 33% chance that I have COVID, despite the fact that my test is really accurate. 99% chance that only positive people test for COVID and 99% chance that negative people will test negative. Even with that kind of accuracy, because as you will see shortly, I'll show you it with numbers, you have only 33% chance. What does that mean? That means this number has to be made a whole lot higher. That is, this 99% is not sufficient. The more, as you will see, you can check this out, the more you keep increasing this number, the more likely that you have. Now, a few other things, because it might be a confusing example, but then how did we, like very quickly, the doctor said, oh, this guy has COVID and they isolated all of us. The reason was there were other priors. The priors were, does this person have cough? Does this person have fever? Is this person showing other symptoms? That's why they collected all that information. Another way of creating a stronger prior. So here, the number that really killed us was this. This is 0.005. If this is 50%, you will get 99% here. Okay, if the prior possibility of you having COVID is 50%, you'll get exactly 99% chance that you have COVID or not. Okay, but since you are giving no information, the prior is that 99.5% I have no chance I have COVID. Just because a test said so, it doesn't mean I have it. The test, unless it's really, really accurate, can really mislead, as I will show you with numbers. Now, what you can do, which is why people did this, you can repeat your RT-PCR test. Now, once you repeat your RT-PCR test, now you have a stronger prior. Your prior now is you have 33% chance of COVID. So this number increases. Then you repeat this. Now you repeat a second time, that number might go up to, let's say, 66. Then you repeat a third time, it might now go up to 99. Okay, so that's how you make more sure, and that's why we repeated COVID tests. So the point here is the prior is shifted by the probabilities that we have calculated. And we will use this again powerfully when we come to inverse problems. So the prior is a very important quantity that you require. If you have no prior, or let's say a 50% prior, then we have got nothing other than simple Bayes theorem. Okay. Now we are going to use numbers. So just to deconfuse or reduce the confusion in this example. So let's say you have, you want to check this out. You want to find out what is the probability that I have COVID, given that I tested positive. So how should you calculate it? What you should calculate is the number of people with COVID testing positive divided by the number of people actually testing positive. Another way of saying it is, this is number of people with COVID and testing positive divided by the number of people testing positive, period. Okay, so let's say we have 10,000 people who go for the test. Okay. Only 0.5%, which is only 50 people actually have COVID. Okay, so now we had 10,000 people, 50 have COVID. Okay, so these 50 people go for the test. How many will test positive? Remember, we have a 99% positive test rate. So 99 multiplied by 50 is 49.5, approximately all 50 test positive. Okay, so this is really good. So we have tested, or 50 people are tested positive. But in these 10,000 people, 9,950 did not have COVID. And out of them, a very small number, only 1% test positive, which is 99.5. So, but 100 test positive without COVID. So 50 test positive with COVID, 100 test positive without COVID. So now what happens? What is the probability? Now you collect these people who have tested positive. Only 50 have COVID, but there were 150 people. So 33% is the chance that you lay among the 50 people who had COVID. Now, if we increase the numbers to how many of these people testing positive had cough, etc., then the numbers change. So I hope it is clear that there is the prior, which is really important. And the prior is what gives you this probability, which is the posterior probability. So depending on how strong the prior is or how weak the prior is, the posterior is strongly affected. And this is why this is both the positive as well as the negative part of Bayes theorem, in that the prior can strongly affect what our results are. And like I said, there are arguments between frequentists and Bayesians about which one is correct, which one is not correct. Nonetheless, you can see that in this example, it's very, very important for us to know the prior before we make an accurate judgment, whether it's in cancer diagnosis or in COVID diagnosis, on what we have, and we can't simply make this decision without Bayes theorem. So I'll stop here and we'll continue with our journey with probability theory in the next video. Thank you.